Assalamualaikum warahmatullahi wabarakatuh. My name is ALIF bin HAMIDIN. My ID number is 2021206878.
Hi, Assalamualaikum. My name is AMIRUL HAQEEMI bin LOKMAN HAKIM, and my student ID is 2021625208.
Assalamualaikum warahmatullahi wabarakatuh. My name is SYABIL MISKAM and my student ID is 2021815228.
Introduction. Self-healing concrete aims to address the common issues of concrete structures such as crack and durability problems. These flaws can lead to leakage, contamination, and corrosion of the reinforcement. Self-healing concrete, specifically the bacteria-based approach, focuses on improving durability and extending the lifespan of concrete buildings. It involves incorporating bacteria and calcium lactate into the concrete mixture. The bacteria remain dormant until cracks form, and when water enters, they become active and produce limestone to fill the cracks. This process effectively seals the fissure. The direct approach of introducing bacteria to concrete is the most popular method for creating self-healing concrete. The objective of this report is to explore advanced material for construction and evaluate the impact of adding bacteria as the healing agent on concrete properties.
Methodology. Firstly, preparation of concrete sample. Then, slump test. Third, compression test. Next, tensile test. And lastly, flexural test. These tests provide valuable information about the properties and performance of the concrete, including workability, compressive strength, flexural and tensile strength. Firstly, preparation of concrete sample. Ordinary Portland cement is mixed with water, aggregates and bacteria. Then, slump tests are conducted to measure the workability and consistency of the concrete. Next, the concrete is then placed into cube and beam molds, and after 7 and 28 days of curing, the specimens are taken out, dry and tested for compressive and flexural strength. The methodology for slump test. Firstly, the representative sample from fresh concrete was taken about 15 kg. Then, ensure the mold was clean and dry inside. The inside and base of the mold was damped using the clean rag at the beginning of every test. The mold was stamped on the smooth hard plate and stepped on the footrest of the mold. Next, the mold was filled by 3 equal layers, which every layer was 1/3 of the total of the height of the mold that need to be tested. Each layer was compacted 25 times by using a tamping rod. After the top layer was tamped, the rod was passing through the top of the mold to smooth off the excess concrete. The outer of the mold was cleaned from concrete. The mold was lifted vertically slowly and carefully, and the mold was inverted and placed near the concrete mold. The rod was raised across the inverted mold to compare the height of the mold and the created mold. Then, the slump of concrete was measured from the top of the concrete to the underside of the rod using a ruler. And lastly, the measured slump was recorded and the type of slumps was determined. Next, compression test. Firstly, the concrete block was taken out and wiped out the surface from any grade or projecting fins of the cube that will be contact with the platen. The dimension and the weight of the specimen was determined and recorded. The specimen was placed in the testing machine and ensured that the surface of the testing machine was clean. The specimen was placed centrally on the testing machine and ensured that the height of the specimen to the top of the machine was not too far. The door of the machine was closed and the data of the specimen was filled in the software of the machines on the computer. The testing machine was started and the load was automatically applied by the machine until it breaks. The maximum load was recorded and the machine was clean. Then, flexural test. The concrete specimen was taken out and wiped out the surface from any grid or projecting fins of the cube that will be contact with the platen. The dimensions and the weight of the specimen was determined and recorded. The specimen was placed in the testing machine and ensured that the surface of the testing machine was clean. The specimen was placed centrally on the testing machine and ensured that the height of the machine to the specimen was not too far. The data of the specimen was filled in the software of the machine in the computer. The testing machine was started and the load was automatically applied by the machine until it breaks. The maximum load was recorded and the machine was clean. Lastly, tensile test. The test specimen must comply with stated requirement, which is shape of the test specimen, material, and allowable dimension. Next, the initial dimension is measured. After that, tensile test apparatus is settled up. Then, the loading shaft is extended slowly by using the handle. Ensure the relief value is fully tight. After that, the main power supply and machine selector switch is switched on. The test specimen is pulled by tensile force until the test specimen is filled. The main machine is switched off. Remove the test specimen from the upper and lower chuck screw. Then, the final dimension of the test specimen where failure occur is measured.
Findings. On table 1, we can see the slump test results, where based on the data that was obtained, the slump height of the self-healing concrete was increased by 13 mm compared to the normal concrete. The presence of bacteria in the concrete will increase the bonding between slump and increase its structure. As the result from the slump test for both normal concrete and self-healing concrete were resulting as the workability condition, which is medium workability. Next, table 2 shows the compressive test after 7 days, while table 3 shows the compressive test after 28 days. Results from the test on the compressive strength at various ages reveal the predicted trend in which compressive strength rises with age. The increase in strength might be explained by the creation of additional hydration products as time goes on, which strengthens the bond between particles. For the 7 days of curing, the specimen of self-healing concrete has the higher compressive strength compared to the normal concrete. The increase of 44.57% is the percentage of increasing in compressive strength, and it shows that the bacteria in self-healing concrete may increase 2 times from the normal concrete on the day 7. Next, the result for 28 days of curing have shown that the same result, which is the increment in compressive strength in self-healing concrete compared to the normal concrete. The value of 21.98% is the value of increment compared to the normal concrete. Unfortunately, the value of increment in compressive strength is decreasing between day 7 to day 28 because the self-healing concrete has achieved its maximum strength on day 28. Table 4 shows the results of the flexural test. By comparing the results of the normal concrete and self-healing concrete, by using the data that have been obtained, the flexural strength of the self-healing concrete is higher compared to the normal concrete. The presence of the bacteria in the concrete mix has increased 40.98% of the flexural strength because of the healing process helping the concrete heal. Finally, table 5 shows the data for tensile test. The result shows that the split strength of cylinders for 28 days by using the tensile test. Hence, the comparison between normal and self-healing concrete can be done based on the data that have been obtained. Therefore, the tensile test of the self-healing concrete is higher compared to the normal concrete. Thus, the higher bacterial percentage in the concrete leads to the higher concentration of calcium ions. As a result, the strength of the concrete can be improved, which is 78.57% by presence of the bacteria.
Impact of self-healing concrete towards economy. Firstly is cost saving. Concrete that self-heal can save owners and operators of infrastructures money by requiring less frequent maintenance and repairs. Less money will be needed for repairs, freeing up funds for economic development programs or other infrastructure improvement. Secondly, opportunities for employment and job creation. The use of self-healing concrete may result in these outcomes. self-healing concrete, development, manufacture, and installation demand skilled labor, experts in research and development, engineers and technicians. This helps the manufacturing and construction industries thrive economically and create jobs. Thirdly, competitive advantage and export potential. Gaining a competitive edge and on the international market is possible for business engaged in the research, development, and manufacture of self-healing concrete. If Malaysia takes the lead in this technology, it may draw the investment, open up export prospect, and second its standing as a center of innovation. This might promote economic expansion and improve the trade balance. It's crucial to remember that the financial experts of self-healing concrete may differ based on elements like the scope of implementation, upfront investment costs, market demand, and regulatory framework. However, altogether, the use of self-healing concrete may benefit the economy by lowering prices, enhancing the effectiveness of infrastructures, and encouraging innovation and job development. Impact of self-healing concrete towards community. Firstly, it increases safety. Safety is improved since self-healing concrete helps keep other infrastructures such as bridges and buildings structurally sound. Repairing fractures and deterioration lowers the possibility of structural failures or collapses, improving community safety. This is crucial in locations with high traffic, public areas, and key infrastructure since failing concrete structures there might put life in danger. Secondly, reduce disruption. Traditionally, concrete maintenance and repair procedures sometimes call for infrastructure closure or limitation, which annoy and disrupt the neighborhood. Roads, bridges, and other structures may be used more smoothly and without interruption since self-healing concrete reduces the need for regular repairs. Thirdly, infrastructure with a long lifespan. Self-healing concrete extends the durability and longevity of buildings, resulting in infrastructure with a longer lifespan. As a result, there are less significant repairs, replacement, and related hassles, which directly benefit the neighborhood. Additionally, it aids in the protection of public property and cultural heritage. It's crucial to remember that education, awareness, and community involvement are essential for the effective deployment of self-healing concrete. Public education campaigns may assist in educating and involving residents in the advantages of this technology and how it enhances their safety and well-being. Impact of self-healing concrete towards the industry. Firstly, it enhances the sustainability. The use of self-healing concrete can help the building sector achieve its environment goals. The need for frequent replacement is diminished by increasing the lifespan of buildings, which allow minimize material consumption and waste production. It may also lessen the carbon footprint resulting from maintenance and repair operation. Secondly, enhance security and dependability. Infrastructure security and dependability might be jeopardized by concrete cracks and structural deterioration. Self-healing concrete lower the possibility of failure and collapses by preserving the structural integrity of buildings, bridges, and other structures. Both construction workers and the general public are safer as a result of this. Thirdly, innovation and technological advancement. To create and use self-healing concrete, researchers, engineers, and manufacturers must work together. This encourages technical development and innovation within the sector, resulting in the identification of novel materials, building practices, and monitoring systems. It may also serve as a catalyst for the advancement of other cutting-edge concrete technologies. It is crucial to remember that issues like cost, scalability, and regularity concern might prevent self-healing concrete from being widely used. However, with further study and development, these issues may be resolved and the entire potential of self-healing concrete might be realized, having a profoundly revolutionary effect on the building sector. Impact of self-healing concrete towards the environment. Firstly, it reduces carbon emission. Self-healing concrete can help cut the amount of carbon emission produced during the building and upkeep of structures. By prolonging a structure's lifespan, it lessens the need for regular replacement, which use a significant amount of energy and resources. As a result, concrete manufacture and delivery produce less carbon emissions. Secondly, is natural resource preservation. Self-healing concrete can reduce the need for fresh concrete manufacture, aiding in the preservation of natural resources. Cement and aggregate extraction, which is necessary for the manufacturing of concrete, can have a major negative environmental impact. Self-healing concrete can reduce the need for more concrete and protect natural resources by making structures more resilient. Thirdly, waste reduction. The use of self-healing concrete extends the useful life of buildings, which lower the amount of trash produced during construction. Significant volumes of garbage and produced during the demolition and replacement of dilapidated structures. Self-healing concrete lessen the frequency of this action, which lessen the environmental effect of waste creation, disposal, and landfill use. Lastly, ecosystem preservation. The use of self-healing concrete can lessen the demand for new infrastructure construction, as fewer natural areas may need to cleared for development. This can aid the preservation of natural habitats, ecosystems, and biodiversity. Maintaining ecosystem benefit a region's overall ecological health. Next, how the materials are being used or possible to be used in Malaysia. Firstly, infrastructure projects. Self-healing concrete may be utilized in a variety of infrastructure projects around Malaysia, including bridges, roads, and structures. Self-healing element can be added to the concrete mixture to assist this building last longer and require less maintenance over time. Next is coastal protection. Self-healing concrete can help with coastal protection projects because Malaysia has a long coastline. Self-healing concrete may be used to build structures like seawalls, breakwaters, and offshore platforms because it can fix minor cracks brought on by wave impact or corrosion brought on by contact to seawater. Finally, high-rise structures. Malaysia has a lot of high-rise structures, particularly in populated places like Kuala Lumpur. These structures can be built using self-healing concrete to increase their resilience and structural integrity. The durability and safety of such construction may be enhanced by the concrete's capacity to self-heal cracks brought on by climatic variation or structural motions. Lastly, infrastructure in corrosive environments. Concrete construction may be exposed to the corrosive elements in some Malaysian locations, such as industrial zones or places with significant humidity. In this condition, self-healing concrete, which can patch fractures and stop moisture and corrosive substance from penetrating, can be employed to increase the resilience and lifetime of infrastructures. Next, what is the current research and development related to the self-healing concrete? Firstly is bacteria-based treatment. One method is adding certain bacteria to the concrete mix. When fractures appears, these bacteria become active and start producing calcium carbonate, which aids in sealing the crevices. Until cracks appear, these bacteria are inactive. Researchers are investigating various bacteria strains enhancing their activation and survival, and enhancing the effectiveness of their therapeutic process. Secondly is microencapsulation. Another strategy is to include healing agents such as polymers or adhesive into the concrete mix by encapsulating them inside tiny containers called microcapsule. This capsule bursts when fractures emerge, releasing the healing ingredients that can fill the fissures and repair the concrete's integrity. Thirdly is self-activating system. Researchers are creating self-activating systems that can detect damage and start the healing process automatically. Bacteria-based healing. One method includes adding certain bacteria to it. This system can detect fractures and start the release of or activation of healing chemicals using a variety of techniques such as embedded fibers or nanoparticles. Fourthly, nanotechnology. Researchers are investigating the use of nanomaterials such as nanoparticles or nanofibers to improve the mechanical characteristic of concrete and enable self-healing features. This substance can fill the microcrack and increase the concrete's overall resilience. Lastly is monitoring and evaluation. To identify damage and track the healing process in real time, researchers are also developing monitoring strategies and sensors. This can assist in determining the efficiency of self-healing concrete and pinpointing any places that need upkeep or additional assistance. Discussion of the report. This test result highlight the greater strength and performance of self-healing concrete when compared to the normal concrete. However, it is important to acknowledge that errors can occur during experiment or test, including human error, instrument error, and natural error. Human errors may result from negligence such as not setting the instrument to zero before readings. Instrument errors can arise from faulty test specimens such as loose locking system. Natural errors can be influenced by unsuitable test surroundings. To mitigate these errors, countermeasures can be taken. Setting the instrument to zero before readings can help address human errors. Regular maintenance of instruments can prevent instrument errors. Conducting experiments in suitable conditions can help overcome natural errors. Overall, the test findings confirm the superior properties of self-healing concrete compared to normal concrete, although measures must be taken to minimize potential errors during experimentation.
Conclusion. In summary, self-healing concrete is an innovative material that improves the properties of concrete. It contains a higher percentage of bacteria, which enhances its strength, durability, and other characteristics. The bond between concrete particles are strengthened, enabling it to withstand forces better. Self-healing concrete extends the lifespan of building and save costs by repairing cracks and damage autonomously. When comparing self-healing concrete to normal concrete, the former, which includes bacteria as a healing agent, exhibits higher comparative strength. This demonstrates that self-healing concrete is an advanced and excellent material for construction purposes. Overall, the test conducted confirms that the self-healing concrete possesses superior properties compared to normal concrete, particularly in terms of strength.